So this is the 2024 Higher Level Maths Leaving Cert Paper 2, question 8. So Tommy makes ornaments from metal and glass. He makes an open metal cylinder with a height of 15 centimeters and a radius of 5 centimeters. The net of this cylinder is a rectangle. Find the dimensions of this rectangle. Give your answer in centimeters, correct to one decimal place where appropriate. Okay, so we're given some information here. We're told that the height is 15 centimeters. And we're told that the radius is 5 centimeters. So all we've got to do here is work out the dimensions of the rectangle. So the height of the rectangle will be 15 centimeters. So one of the dimensions here is going to be 15 centimeters. And the width of the rectangle is just the circumference of the circle. The circumference of a circle is 2 pi r. So it's going to be 2 times pi times 5, which is 10 pi. We've got to give our answer correct to one decimal place. So when you do that, you'll get 31.4. So my answer then is, let's say the length is 31.4 centimeters and the width is 15 centimeters. Okay, let's have a look at part B. Tommy makes another cylinder with a height of 22 centimeters and a diameter of 12 centimeters. This cylinder fits exactly inside a glass sphere. The top and bottom edges of the cylinder touch the sphere. Find the volume of the sphere in cubic centimeters, correct to one decimal place. And it even tells us here to use Pythagoras' theorem. Okay, so let's just put in some of the dimensions that they give us here. They tell us here that the height is 22 centimeters. That means if we were to, let's say, take our radius here and come down to here, if the height of the cylinder is 22, this must be 11 centimeters here. The diameter is 12, so this must be 6 centimeters here. And then we have a right angle triangle here. So our hypotenuse of a right angle triangle is actually the radius of the sphere, which is all we need to find the volume of a sphere. You just need the radius. So let's just do Pythagoras' theorem then. It's 11 squared plus 6 squared is equal to, we'll call it r, so I'll call this r here, squared. So 11 squared is 121, 6 squared is 36, is equal to r squared. R squared then is equal to 30, 40, 57, 157. And r then is the square root of 157. So therefore the volume of a sphere, you can get that from your tables, is 4 over 3 pi r cubed. So that's 4 over 3 times pi times the square root of 157, which we've got to cube. That's all just calculator work, and your answer will be 8240.2 centimeters cubed to one decimal place, which is what we had to do. So that's it. Let's have a look at C. Another ornament is made of 2 cones inscribed in a sphere. The top cone is upright, the bottom cone is inverted. The cones have the same base. A vertical cross-section of the ornament taken through the center of the sphere shows the cones as 2 triangles, ABC. So we've got A, B and C here, and we've got A, D, B here as well, with a common side AB. ABC is the top cone, and let's see, the points A, B, C and D all lie on the circle S, which represents the cross-section of the sphere. The line AB and CD intersect at the point E. The diagram is symmetrical about the line DC. State why the angle CBD is equal to 90 degrees. Okay, so we weren't actually told that the 2 cones are right circular cones, but given that the diagram is symmetrical about the line DC, then we can assume that they are right circular cones. So that will help. State why the angle CBD is 90 degrees. Well, CBD is this angle here. That's 90 degrees because it's an angle in a semicircle. I'll write it out anyway. It just is that it's, you can say that the size of the angle CBD is equal to 90 degrees since it is an angle in a semicircle. Let me just explain it a little bit further. This is corollary 3 of a theorem which states that the angle at the center of a circle is twice the angle at the circle standing on the same arc. And we can see here that the size of the angle CED is 180 degrees, therefore the size of the angle CBD is 90 degrees. So what I'm saying there is that CED, this angle here, is 180 degrees. This is the diameter of a circle. If that's 180, that's standing on this arc here. This angle here must be half of that, 90 degrees, because that angle there is standing on this arc here. Anyway, let's move on to the next part. Hence or otherwise prove that the triangles VCE and DBE are similar. Give a reason for each statement that you make where appropriate. Okay, so let me just copy that diagram down and run through the proof here. So it says give a reason for each statement that you make where appropriate. So you have to make a statement and give a reason for the statement that you're making. So let's start. The first thing I'm going to say here is that the size of the angle, so the size of the angle CEB, by the way, do draw in these vertical lines here, they mean the size of the angle. If you leave those out, you're just referring to the angle itself rather than the size of the angle. So we're talking here about the size of the angle CEB. So CEB, this angle here in other words, is going to be equal to the size of the angle DEB, which is, they're going to be 90 degrees. And this is given because we're told in the question that the line CD divides the diagram symmetrically. Okay, so the next thing we're going to say is that the size of the angle ECB plus the size of the angle CBE is equal to 90 degrees. Why? Because they're angles in a triangle add up to 180 degrees. So what I'm saying there is angle ECB, which is ECB, this angle here, I'm going to say this angle here, plus angle CBE plus this angle here, they must add up to 90 degrees, because this angle here is 90 degrees, so these two added together must be 90 degrees. Okay, so the next thing I'm going to say is, and also the angle DBE plus CBE equal 90 degrees as well. It's for the same reason. So what I'm saying is DBE plus CBE are equal to 90 degrees as well, because this angle here is 90 degrees. So these two must add up to 90 degrees. Okay, so let's keep going. So therefore, here we have ECB plus CBE. Here we have DBE plus CBE. So these two here are the same. So in other words, if these two add up to 90 degrees and these two add up to 90 degrees, this must be equal to this, so therefore you can subtract CB from this side, and you're just left with ECB is equal to DBE. So therefore the angle ECB must be equal to the size of the angle DBE. So ECB, this angle here, must be equal to DBE, this angle here, and I already marked them in as being equal. Dot here and a dot here. So if this is 90 degrees and this angle here is equal to this angle here, and we have a 90 degree as well, these two angles here must be equal. But you can write that out as well. You can say therefore the size of the angle EBC is equal to the size of the angle EDB. So what I'm saying here is that EBC, so EBC, this angle here must be equal to EDB, this angle down here. Why? Because we've shown that two angles are the same in both triangles, so the third one must be equal. So I'm just putting down angles in a triangle. Okay, and then finally, just to state it, therefore triangles BCE and DBE are similar. That's it for part 2. Let's have a look at part 3. The top cone has a radius r and a height h. That is, EB is equal to r and EC is equal to h. The sphere represented by S has a radius of 10 centimeters. Use the similar triangles BCE and DBE to show that r squared is equal to 20h minus h squared. So let me just copy down that diagram again and just write in what we have. We are told here that EB is equal to r. So EB, we're saying here, is equal to r. EC is equal to h. So EC is equal to h. That's from here up to here. The sphere represented by S has a radius of 10 centimeters. So let's say this is the center here. This is going to be 10 centimeters from here to here. And similarly down here as well, 10 centimeters. Okay, use the similar triangles BCE and DBE to show this. So let's draw the two similar triangles. So we have a right angle triangle with a right angle here. This is E, this is B, and this is C here. Now remember that this angle here is equal to this angle, and this angle here is equal to this angle down here. So let's draw the other one then. This is the bottom triangle. Again, I'll draw it in the same orientation. And in this case, this is where C is, and that's going to be equivalent to this angle here, and that's going to be B here. The right angle is here, and that's at E, and out here we've got D. So that angle is equal to that angle there. So they're in the same orientation now, so I can just stick in the dimensions. So E to C is H, E to B is R, E to B is R. Now we need another side here really, so I'm going to look at ED, so that's this distance here. So really, if you look at this distance here, just this little bit of the top triangle, that's actually H minus 10. So that little bit there is going to be H minus 10, just from there to there. That means that ED then, the distance from here to here, is going to be 10 minus H minus 10. And that's it. I think we have all the sides we need. We have corresponding sides. We have this side and this side, and we have this side here and this side here. So I'm going to make a fraction here. I'm going to say here that H over R, that's this side over this side, corresponding sides, going to be equal to R, which is this side here, over this side here. Now this is just 10 minus H plus 10. Minus minus is plus. So this here just becomes 10 plus 10, which is 20 minus H. So let's just cross multiply now. So that would give me, let's see, R times R is R squared, and then we've got H times 20 minus h. So that will give us, we have the r squared on the left hand side, 20h minus h squared. And that's it. Okay, so let's move on to part 4. So hence write the volume of the top cone in terms of h and pi and find the value of h that gives the maximum volume for the top cone. You've got to find the volume of a cone first. The volume of a cone is 1/3 pi r squared h. Now if you remember up here we were told that r squared is equal to 20h minus h squared. So instead of the r squared here we can just put in h minus 20h minus h squared. So let's do that. So the volume of our cone is going to be 1/3 times pi times 20h minus h squared times h. Okay, so let's just multiply this out. So we'll get 1/3 pi times 20h times h. So that is, let's see, we've got 20 over 3, let's say we put the pi there as well, over 3h squared minus, then we've got 1/3 again, pi times h cubed. So it is h cubed, it's pi on the top anyway, over 3, and then we've got h cubed here. Now that's really it for the first part. The next part we've got to find the value of h that gives the maximum volume for the top cone. So in other words, we've got to differentiate and let our differential then equal to, or derivative rather, equal to 0. So it's going to be dv dh. So what we've got to do is we're differentiating v with respect to h. So we're going to take the power, bring it down, and multiply and then reduce the power by 1. So 2 20s, 40 pi over 3 times h. Same here, take the 3, bring it down, reduce the power by 1. The 3 will cancel with this 3 here, and we'll just be left with pi h squared. So that's our differential. So what we've got to do now is just let that equal to 0 to find our maximum and minimum actually. So let's do that. So we have 40 pi over 3h minus pi h squared equal to 0. So this is just a quadratic with 2 terms. So what we've got to do is factorize just by common factors. So let's take out a h here. That'll leave me with 40 pi over 3 minus pi times h equal to 0. So if we do that, we get, let's see, h is equal to 0, or 40 pi over 3 minus pi times h equal to 0. Bring this over to the other side, so that'll give us minus pi h equals minus 40 pi over 3. Divide across by minus pi, and that'll finally leave us with 40 over 3 centimeters. So I have two answers here. I have h is equal to 0 and I have h is equal to 40 over 3. What we were asked to find the value of h that gives the maximum volume for the top cone. Now if you put 0 in here, you'll get a volume of 0, so it's not really going to make much sense to put 0 in there. But what I will do is just test these just to make sure that this is a maximum. And the way you would do that is you would take the second differential. So I'm going to do that over here. So this is the first differential here, the first derivative. So let's take the second derivative. So it's going to be d to v over dh squared. And that will give us, let's see, 40 pi over 3 minus 2 pi h. So what we want to do is put in our x values here just to see which is which. Now I'll just do the 0 just for completeness sake. So let's take h equal to 0. If I was to put that in here, I would get 40 pi over 3 minus 2 pi times 0. So that will clearly give us a positive value here. So this is greater than 0, so that must mean it's a minimum, it's a local minimum. So if we take h is equal to 40 over 3, take 40 over 3, so it's going to be 40 pi over 3 minus 2 pi times 40 over 3. You'll find that this is actually negative. This is less than 0, so that means h is equal to 40 over 3. This is a maximum. This will give you the maximum volume. So I'm not sure if you're required to do that, but that just shows you that it does give you a maximum. So our answer anyway is, we were asked to find the value of h that gives a maximum volume for the top cone. So the answer is 40 over 3. H is equal to 40 over 3 centimeters. This is our answer here. Okay, so that's it for this question.